Hey, well, here we go again. You had a day off, maybe, without hearing my voice. What you finished up with last week was looking at Newton's first law. Then you did Newton's first law lab, and then you did another day of Newton's first law lab, hopefully with me here yesterday. If not, I'm still gone, and I apologize, but that is not my fault. Maybe it is. It's my choosing, I would say. So you looked at Newton's first law. You did the first law lab. You saw many different scenarios that you could explain just using Newton's first law. Well, today, we're going to do a practice problem and then get into Newton's third law, continuing to add to what we know. And my hope is, once again, these laws aren't anything new. We're just continuing to apply them to hopefully newer scenarios for you. Kicking off today here, so please give the sub your utmost respect today. You had them yesterday, you're probably going to have them tomorrow, as we are on an outdoor adventures field trip for these 3 days here. Looking at the question though, it says, what is the acceleration of a softball if it is hit by the catcher's glove to stop with a force of 25 newtons? And it has a mass of 0.25 kilograms. So I'm going to go ahead and ask someone to stop it. You work this problem out to the best of your ability. Remind yourself to be drawing your picture, drawing your force diagram, then doing the math. Go ahead. All right, so let's take a look. Hope you had enough time there. If not, go ahead and stop the recording. But we're going to work through this. It says, what is the acceleration of the softball? That's what I'm looking for. If it is hit by a catcher's glove to stop, so it had a velocity and now it stopped, with a force of 25.0 newtons, and it has a mass of 0.25 kilograms. So let's draw the general scenario. We have a ball that is going this direction with some velocity. Not really sure what the velocity is. The problem doesn't state it, but all I know is it's going that direction with some kind of velocity. It is going into the catcher's mitt. I don't know how to draw a catcher's mitt from here, so it's going to go into something that's going to catch it, the catcher's mitt. Sure, really ugly, but it works. Okay? The catcher's mitt is going to be applying the force on the ball. That force we know is 25.0 newtons. We know the mass of the ball. The mass of the ball is then 0.25 kilograms. So we know the velocity of the ball is the direction of velocity. It's going into the catcher's mitt. When it hits the catcher's mitt, it is coming to a stop. Velocity final is going to be 0 meters per second. So it comes to a stop because of a force of 25 newtons. So that is my picture. Okay? So we're looking for, well, what is the acceleration of the ball? So what are the forces affecting the ball? So let's zoom in. Here is my ball now. It is going to, we'll make it as a circle because it makes more sense, even though I don't like doing that. What is happening? Well, what is the only force affecting the ball? Catcher's glove. So, all right. So the only ball we have, right? So the ball is hitting the catcher's glove. The catcher's glove is hitting the ball. Well, we're looking at the force here. What is the force being applied to the ball? Well, it's from the catcher's mitt. It is hitting or pushing, right, my ball with a force of 25.0 newtons. And that's what's forcing it to come to a stop. There's no other forces going horizontally affecting it, because it was already thrown, so it's going through the air. It is now coming to a stop in the catcher's gloves. If you really want to, we can think about all the other forces that are affecting it, but we're really only going to look at the x direction. But here we should know that, gravity is affecting it downward as well. But we're not working in two directions. We're only going to be concerned with what's happening here in the horizontal direction. Okay? So then let's take a look at the problem. Well, I know the force that's being applied to the ball from the catcher's mitt. That force is going to be 25.0 newtons. I know the mass of my ball is 0.25 kilograms, and it's asking me for the acceleration of my ball. So then I would say, all right, do I have an equation with those three variables in it? I hope the answer is yes. We have force equals a mass times the acceleration. Remember Newton's second law. I want to solve for acceleration, so get acceleration all by itself, so divide by mass. I have force over mass equals my acceleration. It is now a plug and chug problem. So let's plug stuff in and chug it away. So we have 25.0 newtons divided by 0.02, ooh, sorry, I'll erase that, 0.25, 0.25 kilograms. If you do that in your calculator, you should get 100, and keep the beautiful little decimal point because I need three significant figures, 100 meters per second squared. Well, once again, we'll check sig figs. We see that I need 1, 2, 3. I need 1, 2, 3. Therefore, I should have, this one only has 2. 1, 2. My brain stalled. You should have 2 of it. So you can write it in many different ways. You might want 1.0 times 10 to the second meters per second. In this case, I'm not going to be too picky with the sig figs of this problem. I wanted to have 3, so I could leave it as 100, but it does not. So, you get 100 meters per second. What I would start to take a look at here is it positive or negative, and does that make sense? Well, if the glove applied a force to the ball, and the ball was, the force was given to us as positive, and positive must mean to the right then. So this must be positive direction. Therefore, this must be to the right, the negative direction. But the force was a positive 25 meters, and positive 25 newtons, and I am left with a positive 100 meters per second. That means I have a positive acceleration. I would say, okay, well, did the ball slow down then? Well, if the velocity of the ball was pointed that way, it had a negative velocity. If it has a negative velocity and a positive acceleration, does it slow down? Yes. Therefore, my numbers are correct. I like to think through, does my directional pieces make sense? The answer is yes. My ball had a positive acceleration, but it slowed down. Why? Because it was going in the negative velocity direction, the negative direction. And we can see from our picture here that my force is in the positive. Therefore, my velocity must have been in the negative. Those are opposites. Therefore, we slowed down. So that is your problem to work through today. Question of the day. But this brings us to kind of a cool piece, primarily because this problem has two things interacting. We had a baseball and we had a glove. In the past, we worked with Newton's first law. We saying that an object in motion will stay in motion, and an object at rest will stay at rest until they're affected by an unbalanced force. We were talking about an object. When we calculate F equals ma, that is specifically for one object. Yes, we can apply it to two different objects, but so far, we've looked at that. And so we have Newton's second law of the equation, and we have Newton's first law speaking of the interaction of one object, or one object itself. Well, Newton's third law comes into play here, and it starts to say what happens when two of these objects interact. Because a lot of times you have two objects that interact. I played catcher for a number of years. I also was the pitcher for a number of years. And what I know is that when the baseball hits the catcher's mitt, the force of the baseball equals the force of the glove. Because the force the baseball hits the glove with, it is equal and opposite to the force of the glove hitting the ball. They hit each other the same. The ball doesn't hit the glove any harder than the glove hits the ball, but they're in opposite directions. How do I know this? Well, because I know from playing catcher, when you catch a really fast ball, it hurts. And I know my hand might move a little. My hand moved a little, however, the baseball moved a lot because it stopped. Well, if these forces are equal to each other, why did the motion look different? Well, let's look at that, and that's what we're going to spend some time on. Well, because I know that a force is a mass times an acceleration. If the forces are equal to each other, that must mean that my baseball's force must equal the glove's force. And so let's look. Well, if I have my baseball itself is going to have a little mass, and therefore it's going to have a big acceleration. Did it? Yeah, 100 meters per second squared. When it hits my hand, well, the glove is attached to my hand, which is attached to my body, so technically it has a pretty big mass. If it has a really big mass and has the same force, it must have a little acceleration. And that's how the force of the baseball will also equal the force of the glove, but they affect it differently. Why? They're two different objects. They're two different objects with two different masses, therefore, they're going to accelerate differently. My glove moved a little bit. The baseball moved a lot. Why? Because their masses are different. So let's look at Newton's third law. Newton's third law states this. If you were to look it up in your beautiful textbook, it says, when one object exerts a force on a second object, the second object exerts an equal but opposite force on the first object. Once again, you'll hear me say equal and opposite, equal and opposite, equal and opposite. I know it's been taught somewhere, and it is taught. They may call it, they may call it an action, reaction, tear. I cannot stand that verbiage. Primarily because when you hear action, reaction, your brain thinks that one thing happened and then the next thing happened. The baseball hit the glove and then the glove hit the baseball. No, they happen at exactly the same time. Instantaneous. And that's why you'll hear me use the words equal but opposite. They happen at the exact same time. They're equal and opposite forces. So once again, you might have been taught action, reaction, pair. I don't like that verbiage. I think it leads to misconceptions. However, I do think it was probably taught correctly, even if it led to misconceptions. So, what does that mean? Well, that means the force of object A must be equal to the force of object B on A. And so you'll see this here. The force of object A on B must be equal to the force of object B on A. Cool. Opposite. They're equal and opposite. They're two different boxes. Therefore, they have two different masses. Therefore, they're going to accelerate differently, even though the forces are the same. So let's continue to think through this. How can that be? Well, if we take a look here, it says, how can a horse pull a cart if the cart is pulling back on the horse with an equal and opposite force? I mean, didn't we just learn that equal and opposite was a balanced system? Sure, but that was when we were looking at one object. If there were equal and opposite forces affecting one object, we called it a balanced system. Here, there are equal and opposite forces affecting two objects, so different objects. Therefore, it is no longer a balanced system. So let's take a look at why. Well, we have the cart pulling on the horse, and we have the horse pulling on the cart. I know that my horse weighs a lot more than my cart does. Therefore, my cart's going to accelerate. Because I'm pretty positive I've ridden on my aunt and uncle's horse that pulls a sleigh just about every single winter season. Once again, it comes back to this idea that they are equal and opposites, but they affect different objects. Because once again, it's the interaction of two different objects. It is not balanced, even though it's equal and opposite, because there's two different objects. So let's take a look. Let's do an example. Here. Oh, see, I can't stand that. I should have looked at that. I don't like action-reaction pairs. Gag me. Sorry. I don't know why that's on my PowerPoint. It shouldn't be. But it is. So we'll move on from there. I know that when I hit a hammer, I use a hammer to drive a nail into the wall. So the question then demands, which one hits harder? The hammer hitting? Does the hammer hit the nail harder? Or does the nail hit the hammer harder? I hope you're saying, Mr. Ellis, didn't you just say they do it the same? And I would say, yes. The force of the hammer on the nail is equal to the force of the nail on the hammer. They're equal and opposites. They're equal forces, opposite directions. So then why does the nail move? Great question. So let's really look at that. Well, if their forces are equal, we have to start looking at their masses, right? I know that my hammer is going to have a big mass, and I know when I swing my hammer, it hits the nail, it has a little acceleration. Opposite of that, I know my nail has a little mass, and therefore my nail has to have a big acceleration to match it. That is why the nail moves and gets driven into the wall. They hit each other with the equal and opposite force at the exact same instantaneous second, just one had a smaller mass, so the acceleration affected it more. Well, let's look at another example. How spaceships, sick, there again. Let's look at this, right? We have your spaceship going into outer space and your Earth down here. Okay? Well, I know that it says they're equal and opposite forces. True. So the force on that my rocket puts on Earth must equal the force of Earth that it places on the rocket. True. They are equal and opposite. But if you really look at that, my rocket's mass is mass. Therefore, it gets huge accelerations as it then escapes gravity and goes into outer space. Whereas my Earth has a massive acceleration. Therefore, my Earth has a massive mass and a acceleration. Yeah. Does Earth accelerate when you jump? A smidgen. A smidgen in terms of the fact that they notice it. Maybe the ground caves a little bit. There's some change, but the mass is so large that it didn't really move much. Whereas if you look at the rocket, it had such a little mass in comparison, it had a huge acceleration. So once again, both objects are going to accelerate because both objects are applied with a force. Which one is going to accelerate more? Well, if the forces are the same, you need to divide it by the mass. If your mass is really, really little, your acceleration is going to be big. If your mass is really, really big, your acceleration is going to be very, very little. So let's think that through. Okay? Small mass, more acceleration. Large mass, less acceleration. Let's think that through. Mr. Ellis is not the brightest person in the world. I know that, okay? With that being said, he in high school was more competitive to all end. And in high school gym class, decided I was so frustrated because we lost our basketball match that I was going to punch the wall that has the little thin mats on it. Well, I punched the wall super hard. Oh, yeah. But that wall hits back just as hard. Oh, man. That's why it hurts. Because the wall hits back. Why? Because we know that the force of my punch on the wall was exactly equal to the force at which the wall punched me back. Now, looking at that, why does that make sense? Well, because I broke my hand. It hurt. It was really dumb. Well, why? Because my hand's mass is really little. And so my hand experienced a huge acceleration, to which my bones could not handle, and so it snapped as a natural precaution to make sure nothing else gets wrecked. Kind of like the critical zones on cars. Well, looking at that, that brick wall was attached to the building and the school, so it had a huge mass and acceleration. The wall, and if you really were to measure it, might have jiggled. Maybe the brick jiggled. So it still had an acceleration, it just wasn't even in comparison. So who won? I would say I hit the wall just as hard as that wall hit me. I got hurt though because my acceleration was too big for my body's bones to handle. Okay? Think of a football collision, the interaction of two people. People get up, whoa, yeah, I smoked him. I would say, really, did you? Did you really smoke him? I mean, he hits you just as hard as you hit him. I can prove it. There was absolutely no difference from who hit who. You hit each other the same hardness, the same force. Whoop-de-doo. But what might have happened is, looking at either the angle of its hit or the direction, is maybe one of their masses were bigger, so they experienced a smaller acceleration. The other mass was smaller, they experienced a bigger acceleration, right? Your lineman hitting your wide receiver. Your DN hitting your wide receiver. It might look like this guy lost because he accelerated more. I would say, hey, remember, the forces are equal. They hit each other with the exact same force. One had less mass, so it accelerated more. I promise it hurt both of them. I've been on both ends of it. You can hit someone super hard in football and be all excited and still be cringing in pain because it hurts so bad to do it. Because you hit each other with the same force, equal but opposite. Which is why it's kind of scary then when we get in car accidents and follow Newton's first law, what that looks like. All right, I see that we're back. I'm not sure when my recording cut out. I'm guessing I was talking about car accidents. And talking about, well, what the big thing, the big problem is that, well, your car, if you hitting your steering wheel, right? You hit your steering wheel with the same force your steering wheel hits you. But your car's mass is huge because it's attached to your steering wheel, so that's the mass of the car, so it's going to experience little accelerations. However, your body's mass is so small, you are going to experience an extremely large acceleration. Not all the parts in your body can handle that. Your bones are pretty strong. If you break a bone, whoop-de-doo. But if your bone stops hard, if everything stops hard, it's not only your body that's hitting the steering wheel with equal force, but it's your heart hitting your rib cage, or your lungs hitting your rib cage with that equal force. And we know that some of those objects cannot withstand this acceleration. So even though our forces are equal, because the objects are different, we experience an acceleration that is different. And that's where we start to see why things move the way they do. So, that is Newton's third law. We talked about Newton's first, you did labs on it, you did a lot of stuff with Newton's second, did calculations. We used Newton's second to then show you calculations here for Newton's third law, because Newton's first and Newton's third law are really just conceptual thinking. Can you think through the scenario, the problem at hand, whereas Newton's second law is the calculation part. So please make sure you're getting your work done. You have everything you need to know now for your test, so it's practice, practice, practice. Read your book, do the questions, come in with questions when I'm back, and get ready for your test. All right. Have an excellent night. Please give your utmost respect to your teacher. Please be working through the homework. You should now be able to finish the More Forces worksheet that you're going to be getting today, because that has Newton's third law on it. Tomorrow you'll start getting one of Newton's laws explains, which means now we're going to use all of Newton's laws and try to explain scenarios that take place using them. So, have an excellent rest of the night.